Good. Then welcome everybody to the afternoon session of FPSAC 2021, although it's 2022. So if you're in the wrong meeting, there's still time to leave. Otherwise, we're looking forward to a number of great talks, starting with the invited talk by Karola Mészáros on Schubert polynomials from a polytopal point of view. If you have any questions, please put them in the chat. And I was told all the co-authors will try to answer them. And those that don't get answered, I will relate to Karola either immediately or if it works out towards the end. All right. So Karola, take it away.
Thank you, Raman. And thanks for the organizers for organizing this exciting conference. And I want to say a big hello to every of my friends and colleagues that I know, and I miss you. And hello to everyone I don't know, and I hope I get to meet you in person in the future. I also want to thank my wonderful collaborators, many of them, who have helped me on this journey on Schubert polynomials and connecting them to polytopes. And I'll sample some of the work with some subset of them, in particular with Alex Thing, Jun Ha, Ricky Liu, Jacob Materna, Linus Satyabrat, and Avery Saint-Nazaire. And I should also thank Avery so much for many of the wonderful slides that are here. So let me give you an overview or just a main idea of what I'm going to think about. So we'll be dealing with some polynomials. So let's just take a polynomial in 3 variables at first. And we're going to have integer coefficients, they will be non-negative. So let's take, for starters, x2, x3 squared, plus x1, x3 squared, plus x1 squared, x3, x1 squared, x2, plus x2 squared, x3. Okay, so let's start with this polynomial. And the way I will think about this polynomial is really in terms of the exponents. So this monomial for me will represent a point in 3 space. It will be 0, 1, 2 by this exponent. Here it will be 1, 0, 2, 2, 0, 1, 2, 1, 0, and 0, 2, 1. I must be missing a 6th one here. Let's see, so who am I missing? So I'm looking at all, I mean, I don't have to be missing, but I want to take all the permutations of 2, 0, 1 as exponent vectors. So I am missing 0, 2, 1, 2, 0. So x1, x2 squared apparently wasn't on my list, but it should have. Okay, and so now I have these 6 points in space. They are in 3-dimensional space, but they sum to, the coefficients sum to 3. So really they are on a 2-dimensional hyperplane. And so we can plot them. They're going to form a hexagon. So I'm just going to write without the commas points here. And so if I'm just thinking about the support of my polynomial, this particular polynomial, the support will be these 6 points. Something to note, if you think about polytopes, you might think about their integer points that they contain. So in this case, we have another integer point in our lattice inside, and that's 1, 1, 1. Okay, so maybe I will add also, if I add the monomial x1, x2, x3, then I actually get all the integer points of my polytopes enclosed. So I saturated it. Now this polynomial that I considered here is very special. It has only 0 and 1 coefficients. So this picture actually encompasses it all. But maybe I have a coefficient of 2 with some monomial. So then I will have to embellish my picture with the coefficients. Otherwise I lose track of the polynomial and I only remember the support from the picture. So if I want to remember everything, I will have my integer points in space endowed with the coefficients. And so this is the idea of how we'll think about polynomials today. In particular, we'll talk about Schur polynomials, which I'm sure are very familiar to many of you, but we'll start with them. Then we'll talk about Schubert polynomials that can be seen as generalizations of Schur polynomials. Schur polynomials are Schubert polynomials of Grothendian permutations. And then we also talk some about Grothendiec polynomials. And it will be most of what I'll say be in this kind of polytopic language, but not everything. Some will connect to posets and other combinatorial objects. All these polynomials are important in algebra, but we'll take polytopic point of view. Okay, so that's sort of what we'll do, and let's just get to it. I know this is familiar to many of you, but I want to quickly go over. So we have this tableau. So we are defining Schur polynomials. This is the combinatorial definition. So our tableau are of shape 2, 1, 0. This 0 and the end, if you like, you can add this thing, but it's just really indicating that the length of this partition is 3, and we'll be filling our tableau with 3 integers 1, 2, and 3. And so we put 2 boxes for these 2 to the left, and 1 box, and then 0 boxes. And we are filling it with the numbers 1, 2, 3, so that the entries are weakly increasing left to right in each row and strictly increasing in the columns. And so we get so a Schur polynomial indexed by this partition 2, 1, 0 in 3 variables corresponding to the fact that this partition is of length 3. We simply do this generating function. So if we have 2 1s in a tableau and 1, 2, that will yield x1 squared, x2, etc. So we sum up all these things. So if you might notice that this is actually the polynomial I was considering on the very first page. So these guys are symmetric and they are very important. They are basis of the ring of symmetric polynomials. And then Newton polytopes is the, we also already met in the first slide, but we didn't call them this way. So if you have a polynomial, you can think of the exponents in space like we did. In this case, it's a 2 variable polynomial, and plot the exponents in space of the terms with non-zero coefficient and take their convex halves. So Newton polytope encompasses is the smallest convex polytope containing the support, but it doesn't determine the support necessarily, as we see here, right? These points are not part of the support, but yet they are in the Newton polytope. And it doesn't determine, of course, the coefficients, but it can sometimes determine the support, at least in special cases, if we are hitting every single integer point inside, like we did at the beginning when we added that dot in the middle of the hexagon. And so, question about Schur polynomials, which have been around for a while, right, is their Newton polytope. So I'm presenting 2 of them here. This is the picture from the first slide. So this is actually the Schur polynomial of the partition 2, 1, 0. And something that we might note, right, on these pictures here are the edge directions, right? So this is really the point 1, 2, 0. And this is the point 0, 2, 1. And so this edge direction here is can be seen as E1 minus E3, right? where EI are the standard basis vectors. So it's in a root direction. And then similarly, if you look at the other directions, let's look at one more. Here we get E1 minus E2. So we'll get E1 minus EI minus EJ in general. These are very special polytopes with these edge directions. And so far on this picture, it appears, but who knows, well, we'll answer it, we know, that all the integer points actually correspond to monomials with non-negative coefficients, which would say that these polytopes capture the support, like they actually tell you what the support is, if not the coefficients. So theorem of Rado from 1952 can be interpreted as saying that the Newton polytope of the Schur polynomial indexed by partition lambda is the permutahedron P lambda. The permutahedron P lambda is simply, take the partition indexing your Schur polynomial and permute the entries of that partition in any way and take the convex half. That's the permutahedron P lambda. So the coefficients have a name of the Schur polynomials are called Koska numbers. So by our combinatorial definition of Schur polynomials, the Koska number lambda alpha is a number of semi-standard Yang tableau with the shape lambda that is indexing our partition and a particular weight alpha. So let's say our weight alpha is 1, 1, 1, so which says we are using 1, 1, 1, 2, and 1, 3 to fill our tableau. Well, there's 2 ways to fill it to satisfy our rules. So the Koska number is 2, corresponding to this coefficient 2. For every other monomial for this particular Schur polynomial, there's only one semi-standard Yang tableau of the given weight, which is why the coefficients are 1. And so a natural question sort of from this point of view is asking, well, let's look at the Newton polytope of the Schur polynomial. Can there be zeros inside? Is there an integer point in the Newton polytope of S lambda, which is P lambda, which yields a term with 0 coefficient? Sorry, something happened to my mouse. Okay, good. And so this is a definition of Monickel, Toxin, and Young. They decided to call the Newton polytopes, where every integer point yields a non-zero term, saturated Newton polytope. So a polynomial is said to have a saturated Newton polytope if every integer point in the Newton polytope yields a monomial with non-zero coefficient. Yields a term with non-zero coefficient. And they proved in this paper in 2017 that Schur polynomials indeed have this property. And they proved it for a host of other polynomials as well as conjectured for them. And then once we have this, that we know that this is a saturated Newton polytope, so every integer point, as these are here the coefficients representative of the Schur polynomial here, then we know that they are all non-zero. We can ask about, well, but how are they distributed? If you look here, they surely look as though, like, if you put some heaps of coins or something on top, that you have this kind of mountain shape, right? They are 1 outside, go 2, 3, they grow. Okay. So something that we'll formalize here is we will look in root directions, EI minus EJ. It's natural since we have generalized Permutahedra with these very special edge directions as well. And we will ask and answer whether these coefficients in these particular directions are unimodal or log concave. Okay. So just a quick reminder. Unimodal sequence is one that increases weakly and then decreases. And log concavity is this condition. And if you have a log concave sequence with no internal zeros, here we are dealing with non-negative numbers, then it implies unimodality. So our question to start with is, are these Koska numbers unimodal? Are they log concave? And so rephrased in terms of the log concavity of Koska numbers, it's this inequality where lambda is fixed and we are varying the weight in the root directions. And so I just want to take a short detour here to Littlewood Richardson coefficients. I don't want to dwell on them as they're not the main aspect here, but they tie in nicely here. So I'll just say a few words. But first I'll say that yes, this log concavity holds. This is this corollary. And later on, hopefully I'll get to this more general statement about the Lorentzianness of the normalized Schur polynomial. But the corollary that we are hitting on here is the unimodulity of Koska numbers. And the short detour for Littlewood Richardson coefficients is, which are important to representation theory, and but purely in the Schur basis, we can see them as a structure constant, since we here is that there was a saturation conjecture, probably the one that gave Monickel, Toxon, and Young the idea to call it the saturated Newton polytope, about these Littlewood Richardson numbers saturating a cone, in this case, on the polytope, an infinite cone. And this was proved by Knudsen and Tao in '98. And then there was this conjecture of Okonkos from the early 2000s about discrete log concavity of the function, which soon after its publishing, got a contraexample. But what I want to note here is that this inequality on the unimodulity of the Koska numbers is actually a special case, in which case Okonkov's conjecture holds, because the Koska numbers can be seen as certain Littlewood Richardson numbers. They are, and you can decipher the bijection based on the colors probably. And so really sort of takeaway is that sure, so the conjecture doesn't hold in general, it doesn't hold in any directional line. So the lines on which they were shown to be, it was shown to be false, as if you just take the line from the cone straight out. But there are other directions in which it holds, and it would be interesting to know, to characterize which directions it holds in. And I have no answer to that, but I know it holds for the Koska numbers, so it holds in certain special directions. So moving on to Schubert polynomials, they were introduced by Lascoens and Berger some now 40 years ago. I still keep thinking it's 30, but I guess it's 40. And this is the formal definition, but we'll use a combinatorial definition. So probably I'll just skip over this one. And as I mentioned, Schur polynomials can be seen as special cases of Schubert polynomials, or special permutations. They are associated to permutations. And well, again, they have algebra geometric motivations. Something that Lascoens and Berger immediately noted is that the coefficients were non-negative integers. And so it, of course, begs the combinatorial question, or begs the answer to the combinatorial question of, well, what do they count? And so I want to give you a sample of these combinatorial models that there are now, but there are many others. The first one, due to Billy Jacques's study, was in terms of the compatible sequences. The one that we'll use today, also called RC graphs or reduced pipe dreams, is due to Bill Bergeron and Fomin Kirillov. Then there were corner diagrams, or there are corner diagrams. Newly, there is bumpless pipe dreams, really exciting. And I love personally Modjar's not so widely used combinatorial model that generalizes really the Young tableau definition of Schur polynomials that we have seen. But we'll mostly be dealing with reduced pipe dreams today. So I better define them. So we have our permutation. In this case, it's 2, 1, 4, 3. We write it down the, what's that column? And then we put the identity here, 1, 2, 3, 4. Okay. And our call, we will be placing these crosses and elbow tiles only in this upper half of the matrix. And in such a manner that 1 ends up being connected to 1, 2 to 2, 4 to 4, and 3 to 3. Yeah. And the pipe ring will be called reduced when no two strands cross more than once. Okay, so 2 strands should cross 0 or 1 time, and it's a reduced pipe ring of this permutation. If we have strands that cross more than once, which we'll ultimately get to, we need to ignore the second crossing as we are tracing them from the num I to the I. And so beautiful theorem of Fomin-Krylov and Bergeron-Billy is that if we take the set of all reduced pipe rings, because there's more for any one permutation, and I'll give you an example in a second, and weight the crosses by row numbers, we get the Schubert polynomial. So in this case, we are looking at the Schubert polynomial of 1, 4, 3, 2. There's a total of 5 reduced pipe rings for this one. It's a basic property of these pipe rings that we'll always get length of this permutation many crosses. So in this case, 3 crosses in every pipe ring. And to get the Schubert polynomial, we will simply collect the row weights of these crosses. So this pipe ring will give us the monomial x2 squared x3. This pipe ring will give us x1, x2, x3, because there's 1 cross in row 1, 1 cross in row 2, 1 cross in row 3, etc. So we get 5 monomials here, 1, 4, 3, 1, 4, 3, 2. Coefficients here happen to be 1. That won't, in general, be the case. But definitely they'll be non-negative integers. And a very nice theorem of Bergeron-Billy actually tells us how to generate all of these pipe rings. So very useful in many applications. I'm not sure why my mouse keeps moving or where it even is. Okay, it's here. Good. Grothendiecks polynomials, again, Lasconchurch and Berger introduced them 40 years ago. It's just a formal definition. We won't worry about it. Rather, we'll think about them in terms of non-reduced pipe rings. So as I mentioned, well, you can actually allow your pipes to cross more than once, but then you have to trace the lines a little differently. And since we won't work so much with these, we won't get into details, but it's the same way we collect the weights of the crosses by the rows, and we get the Grothendiecks polynomial. It's a signed sum of weights. The Schubert polynomial is the lowest component. And later on in the talk, I'll talk actually some about the supports of these Grothendiecks polynomials, which a lot of which we don't know yet, but maybe we have some insights. Now, for now, I want to mention a very nice construction of Knudsen and Miller from the early 2000s about the pipe dream complex. So these pipe dreams very naturally fit into a simplicial complex. The facets are labeled by the reduced pipe dreams of a given permutation, and the interior faces of this simplicial complex are labeled by the non-reduced, well, the reduced and non-reduced, so all the pipe dreams of the given permutations, and then the boundary, we get all the pipe dreams of permutations bigger than the fixed one in our in the Bruch order. Anyhow, we won't need so much the structure here, but I did want to show you it's a very nice and important construction. And so far we have kind of glimpsed, well, more than glimpsed at Schur polynomials, defined Schubert polynomials in terms of pipe dreams as well as Grothendiecks polynomials. And so we know the degrees here, and these are Grothendiecks are inhomogeneous. Recently they're top degree has been established to be the reg of W in recent work by Karola, Spire, and Weigand. Hopefully I'm saying it right. And the lowest component, of course, is the Schubert, which has degree length. So let's go on to Newton polytopes of Schuberts now, right? We have looked at Newton polytopes of Schurs. So it's only natural to look at Newton polytopes of Schubert. So here's one picture. And if I zoomed onto any one of the edges, I could show you that each has direction EI minus EJ. And so a natural conjecture by Monickel, Toxin, and Young in their 2017 paper, where they introduced this notion of saturated Newton polytopes, was that the Newton polytope is some sort of extension of the permutahedron, and they gave inequalities actually precisely describing what they conjectured was the Newton polytope. And so I want to mention generalized permutahedra. These are these polytopes with edges in directions EI minus EJ. They've been studied for a while. Edmonds looked at them in 1970. He called them polymatroids. And then Postnikov sort of rediscovered them and reintroduced them to the algebraic combinatorics community under the name of generalized permutahedra, since they generalized permutahedra, like the regular permutahedron where you just permute the components of a vector and take the convex hull. That also has edge directions EI minus EJ, and here the vertices no longer are of that shape, but the edges are all in the direction EI minus EJ. And so a theorem addressing this conjecture of Monickel, Toxin, and Young in joint work with Alex Fink and Avery St. Dizier is that Newton polytopes of Schubert polynomials are indeed a generalized permutahedra. So let me show you just a picture and maybe explain, well, not the proof, but the idea of the proof here on this picture. So the picture corresponds to the permutation 21543. I'm going to draw down and define by example the Rothe diagram of a permutation. Okay, so I need to make a 5 by 5 matrix here. Okay, managed, sort of. And so I write the permutation to its left, 2, 1, 5, 4, 3. Now I will put a dot in the second column because there's a 2 to the left here. I'm going to put a dot in the first column because there's a 1 to the left. 5, 4, 3. Okay, so I crossed out a bunch of the entries, and the Rothe diagram of this permutation are these squares that remained not crossed out by these red rays to the right and the left of my dots. Those dots you can think of as where the ones who go in your permutation matrix. And so now what's happening for any permutation, not just for this one, is we can break down the whole. We are able to break down the Newton polytope of any permutation into the Newton polytopes, the Minkowski sum of the Newton polytopes of matroid polytopes corresponding to the columns. And the way we define these matroids, you just take your boxes and you float them up. Well, actually, it's not us who define them, rather Krashievich and Pragatz. And so, well, in this case, it's very simple. We got the uniform matroid here on one element with less than or equal to 1. This is empty. And this is uniform matroid, 4 elements with 2, well, with 2 elements in the basis on the elements 1, 2, 3, 4, and here our elements are 1, 2, 3, and we have one element. And so we are just summing these matroid polytopes. In general, we are summing matroid polytopes here, not necessarily uniform matroids, because they are uniform because it happens that in this permutation, the boxes are always stacked to the bottom. But of course, you might have, in a general permutation matrix, you might have the Rothe diagram be like this, and these are crossed out. So that won't be a uniform matroid, but there's still a matroid polytope there that we are summing. Matroid polytopes are generalized permutahedra. The sum of Minkowski sum of generalized permutahedra is a generalized permutahedron, and that's effectively done. So we know an exact description based on the Rothe diagram of the permutation of the Newton polytope of the Schubert polynomial. So it makes sense to question the same thing: is how are the coefficients distributed? Well, we also prove that they are, well, saturated. Well, the first question is, can there be zeros? And indeed, that was the saturatedness statement, right, of Monica-Clarkson and Young. The question is, does it have a saturated Newton polytope? And so they proved it for Schur polynomials, and they conjectured in their paper about Schubert polynomials, key polynomials, double Schubert polynomials, Grothendiecks polynomials. These are just some of my favorites, and then more. And this is from 2017, okay? And these are the theorems, and as far as I know, there hasn't been any further progress. So I hope that maybe 5 years on, there might get something. So this was all the results are from 2017. We proved, that Schubert polynomials have saturated Newton polytopes, key polynomials have saturated Newton polytopes. We also proved that one dominant Grothendiecks polynomials have. That's actually via follow polytopes, but I won't talk about that. And then Escobar and Young proved in joint work for symmetric Grothendiecks polynomials using Leonard's expansion for these in the Schur basis. So we have a very specific and concrete description of the support of Schubert polynomials. They are integer points, they are all integer points, so everything is hit, of a very particular generalized permutahedron that we can describe as the Minkowski sum of matroid polytopes corresponding to the columns of the Rothe diagram. So it's only natural to wonder, what happens to the support of Grothendiecks? Before I go into a very specific conjecture, I do want to mention that there's a conjecture about, well, much more than just the support of Grothendiecks. So with June Ham, Jacob Matherna, and Avery St. Dizier, we proved, and I showed you the result, that Koska numbers are log concave. It's a corollary, that's a corollary of the normalized Schur polynomial being Lorentzian. We also conjecture with them that the homogeneous components or normalized homogeneous components of the Grothendiecks, or if you want, the normalization of the homogenized Grothendiecks with positive signs, is Lorentzian, which encompasses that we expect all these Newton polytopes to be saturated generalized permutahedra. It encompasses actually more. We expect the coefficients to have log concavity properties, but just in barely on the support, on the level of support, generalized permutahedra, generalized permutahedra everywhere. But instead of talking about that geometric point here, which is very exciting, I want to actually show you a pulsate structure, which is also quite interesting as a conjectural thing. So remember, these are Grothendiecks in terms of pi primes. This is our Grothendiecks polynomial. And this is our Rothe diagram, right? Again, right, how did we do it? Like, we put the permutation here, and we put the dots in the corresponding column and axis out. Okay. So one thing that this theorem, which is joint work with Linus Settier-Bretta and Avery St. Dizier, says is take this Rotha diagram and take everything above it. So add these guys into it. Together, this is d of w bar. So just look up everything in there. Now the monomial corresponding to this, so x to the dw bar is, well, weight by the rows, right? It's x1 to the third, x2 to the third, x3 in this case. And so the theorem says any monomial appearing with a non-zero coefficient and your Grothendick has to divide x to the dw bar. So if you look here, of course, it will divide. Okay, well, let's take this further. Let's write down by component-wise inequality on the exponent vectors, the Hasse diagram. So here I mean 3, 2, 1, well, 0, 0, because this is an S5. So then this corresponds to the monomial x1 to the third, x2 squared, x1, right? So no, x3 is this guy. And this one corresponds to x1 squared, x2 third, x3, right? And then this second level corresponds to, well, this homogeneous component. And finally, this is just the bottom, the Schubert part. Okay. If you actually checked, you do have everybody here. This is an induced subposet of a poset of multisets, if you like, or a product of a bunch of chains. And well, of course, above here, somewhere, you know, since it's, I didn't put in here because x to the dw bar doesn't appear, but in terms of the poset order, it would be right above them. But we are taking an induced subposet that's induced by the Schubert exponents and the top of the Grothendick exponents. Okay, so let me state. Now this is the formal definition of our poset. This is the relation on our poset, right, component-wise. And so I'll give you a sequence of conjectures, some of which we know how to address in special cases like Fireworks permutations or Grassmannian permutations. And Cornell PhD student Elena Hafner has proved some of these conjectures for vexillary permutations. But in general, these permutations or these conjectures are work in progress, open for any sites. So, okay, so the mildest one, and we'll go in increasing excitement and increasing ambitiousness, is to say, well, if you have somebody in the support, so looking at some exponent, right, in the support of the Grothendick, and it's the degree is less than the total degree of the Grothendick, so less than the reg of W, then there's got to be something else in the support that is bigger than it in this component-wise order. So saying, if I look at 3, 1, 1, I expect, in this case, 3, 2, 1 to appear. I can increase one of the, well, okay, no, this says somebody higher. And the next one says I can actually increase just one, so I can increase one of the coefficients and go up. And then the last one says, well, actually take any two that are in the support and you'll find somebody in between. So really you're getting the whole induced subset here of the poset of multisets. So that's sort of the conjecture. It seems strikingly simple. You have the top of your Grothendick, you have the bottom, everything in between has to be in it, what this conjecture said. As I said, we know this in special cases like Fivers, Grassmannians, or vexillary. Well, not even actually not the whole conjecture, just maybe some gradation. But as far as we could tell, and as far as we were scratching our heads with all the combinatorial models, it's not obvious. Going down, of course, is obvious. Like with pi-brims, you can go downwards. Anything, you take anything, you can go down because you get rid of a cross, right? That's how it's engineered, but this is going into the other direction, going upwards towards the Grothendiec, the top of the Grothendiec. Now, of course, when you have a poset, heck, you know, what's the first thing you think when you think of a poset? Well, the first thing I think of a poset, I think of the Möbius function. Okay. So let's just do some seeming magic here. I have no insight. I just want to show you the magic. Or no real insight. So this is our poset. Let me write down the coefficients corresponding to the monomials with these exponents. Okay, so this is 1, 4, 3, 2. So this is 1, 1, 1, 1, 1, corresponding to these. Okay, so the exponent 1, 2, 1 has a coefficient 2. 2, 2, 0 has a coefficient 1. Sorry, not the 0, 1. And then 1, 2. Oh, wait. What happened here? No, I must have done. Yes. Oh, this was this one. Sorry. I kind of went ahead of myself, and this is also a 2 here. Okay. And then finally, this one is a 1. And so what I want to note is, well, let me add a minimal element with a so a minimal element to this poset. So the Möbius function of now this poset with the 0 hat included. So 1 is of course 0 hat, 0 hat. These ones, well, maybe I'll make them the negative ones, and I make this into negative 1. And what you get here is that these are the Möbius function values of 0 hat, comma, your element. Now all I did, I took the negative of, of the Grothendiec. Of course, this kind of manipulation or hope that this will be the Möbius function only makes sense if your Schubert polynomial was 0, 1, because if you have any 2's here and you connect the minimal element, like forget it, right? So let's look at a slightly more complicated example. Okay, so here's this permutation. I drew the poset with the 0 hat included. And actually, I didn't draw it, Avery did. And these are the Möbius function values. And sure enough, if you check, they match the coefficients of your Grothendiec. This one here corresponds to x to the dw bar. dw bar is 3, 3, 2, 2. It does not appear in the Grothendiec. So, well, it says it appears with coefficient 0. And so maybe I won't recall this rather because I'm running sort of behind myself. But I'll say that we tested this up until and including S8. And it appears that when your Schubert polynomial is a 0, 1 polynomial, then your Grothendiec is simply the negative of the sum of this. So it's kind of like a generalized characteristic polynomial of your poset. Certainly intriguing. I'm not sure where it may be coming from. Okay. And when it's a general permutation, we still have some sort of more limited Möbius-like conjectures, but I will kind of, since we don't have real insights to offer, I will just stay with this one, which seems rather striking. Okay. Of course, it could be that contrary examples come in S12, but nevertheless, it appears that there's definitely some truth to this. Okay, so now with that, since we were already at 0, 1 Schuberts, right, this conjecture 0, 1, let me say that we know who 0, 1 Schuberts are. Okay, we can characterize them. Well, first of all, polytopally, what does it mean to say that we have a 0, 1 Schubert polynomial? Well, it means that the Schubert polynomial is the integer point transform of its Newton polytope. It means that because we know that the Newton polytope is saturated and Schubert polynomials have integer coefficients, okay? So in other words, and this is how this question actually occurred back when we considered it, is we wanted to know when is the Schubert polynomial, the integer point transform of its Newton polytope. Well, we already went through Rother diagrams, right? And so we wanted a diagrammatic condition on the Rother diagrams that characterize 0, 1 Schuberts. And it turns out that if they avoid these configurations, then they are 0, 1. This is joint work with Alex Fink and Weber is saying this here. And so, for example, right here, we're saying this is not a 0, 1 permutation at all because all the configurations appear. Now, these are configurations. Maybe we want pattern avoidance. It's not difficult to translate these configurations into permutations. So there happen to be 12 permutations who we need to avoid in order to be 0, 1, and it's these 12. And something nice that comes from the proof that I think is interesting on its own is the following. So, so we are really looking at patterns. When we look at patterns, it's, well, we think in terms of Rother diagrams, so we better think about patterns in terms of Rother diagrams. Well, getting a pattern of a permutation is the same as focusing on one of your red dots and then crossing out the row and the column of red dot and then just getting rid of that. So that gets you the Rother diagram of the pattern. And so with this view, something that we proved is that the pattern, the Schubert polynomial of the pattern, is in a sense contained in the big Schubert polynomial. Indeed, if we take the big Schubert polynomial and get rid of these row and column here, these are the boxes we got rid of, so that gives us this monomial x3, x4, they weighted by, again, always by the row number. And then we get the pattern of sigma, but now, since it really lives within d of w, right, and we got rid of x5, it's going to be evaluated at x1, x2, x3, x4, x6, x7, right? We skipped row 5. And so we're saying this is non-negative. I think that's a really nice thing on its own. And it tells us that if you have any on the pattern containment, right? So if you contain a pattern and your Schubert polynomial of the pattern has a coefficient 2, then your bigger one will also have that or even bigger coefficient. So it's, you know, this wondering about the coefficients really is tied to the pattern containment. So if you wanted, yeah, and that was key in looking at these 0, 1 Schubert polynomials. And sort of the final question is, how are the coefficients distributed? So we know there's S and P, we know what the Newton polytope is, but how are they distributed? Right, we looked at these unimodal and log concave things at the very beginning. So how are they distributed here? What we have is sort of the perfect setup here if we are in 2018. You know, we have generalized Permutahedra as Newton polytopes. We know that they are saturated, and we want to prove that we have log concavity. And so the question is, what do we do? Well, Brandon and June Ha introduced Lorentzian polynomials about the same time, which indeed encompass all of these three things. So then what to do is to prove that these objects, the Schurs and the Schubert, or their normalizations, are Lorentzian. I don't think I quite have, actually, how much time do I have, Raman, so I know where to skip?
I guess about -2 minutes.
-2, oh great. So I don't have time in this -2 minutes to go through the Lorentzian property, But I think that this picture is actually very much what I would take away from it. Saturated Newton polytope, generalized permutahedra, log concavity is what you want. You wonder Lorentzian polynomials. And so what we prove indeed is that the normalization of Schur's is Lorentzian. We conjecture that the normalization of Schubert is Lorentzian. We prove something else. We prove that the normalization of some sort of transformation of the Schuberts is Lorentzian, which is enough to say that the coefficients are log concave, right? Because we only, if you look at this and you're a polytope person, you only like flipped around and I don't know what you did with your polytope in space. You didn't do anything to the coefficients. They're still along the same lines. So we know that in the Newton polytope of the Schubert polynomial, along root directions, you have log concavity. And that's a very satisfying thing. As I said, there's more general conjectures for Lorentzianness of Grothendiecks and log concavity and polymatroids and everything else. And we don't have a purely combinatorial proof. I have failed at it. And I will say thank you for listening.
Okay, thank you very much for this wonderful talk. So there is so far one question in the chat, which is a little general, namely whether your conjecture on this generalized characteristic polynomial for Grothendieck polynomials that you showed is related to a result of Knudsen on, there's even a link to a paper, Frobenius splitting in Möbius inversion.
So the answer is, I doubt, but I don't know. I don't know the answer. I think I might not know the paper. I have asked Alan about this conjecture, and he did not give me that paper, so I doubt, but I don't know.
Okay, so there's one raised hand, but I'm not sure how this works with recording the talk and the questions. Maybe it's easier to ask it in the chat.
Oh, I would love to see someone ask a question. Although Raman, I love you reading it too.
By all means, they can unmute themselves and ask it. There is
all
still
right,
time.
Even better. It gives more of a feeling that there are people in the room. So please, if you have a question, raise your hand, ask the question. Yes.
Hi, Karola. Thanks for the lovely talk.
Who am I talking to? Hello, I don't see you or know who you are.
Oh, sure. Zachary Hamaker here.
Oh, hello, Zachary.
Hi. Can you go back to your conjecture about the poset structure on monomials for Grothendieck's?
Yes, I'll be there in a second. Well, this is fine as well. No, actually. Oh, yeah, it's fine. This is fine.
You had a poset before this. I thought you had a previous conjecture just about.
Yes, I did have, and that was for every permutation.
Yeah.
Is it this one that you're thinking about? Maybe.
Yeah, and so.
Or maybe this one doesn't really matter.
Yeah. So if I'm understanding this right, the conjecture is basically that. So every monomial divides a maximal degree monomial. Is that?
You could phrase it that way as well.
Yeah.
Yes.
Have you tried to?
It's more. It's that you find all of them. It's like that you look. Let us say you zoom here at 301. Okay. And you zoom here, and there's a path. I guess that maybe I shouldn't say it that way. Maybe I should say that every I think what you said is maybe the best way to say it. Yeah.
Okay, so I guess what I'm wondering is, have you tried to describe what this conjecture means in terms of the subword complex interpretation of monomials?
Right. So yes, but the sort of first hope would be, right, that you can just like add crosses in pipe dream complexes, that you can just add crosses and get to a lower dimensional face that way. But the truth of the matter is that that doesn't happen. So should I have an example? Because I thought this would be a very natural question. So for example, this is a projection of the subword complex or pipe dream complex or 1, 4, 5, 2, 3, right? So for example, if you start, so this is the whole thing, this is a ball, you start with this edge, right? Its vertices are on the boundary, but you want to get to this vertex. So you can't simply add crosses. You have to shove around the crosses in your pipe dream and end up here. So I would say that I don't see, because of these kind of issues that can come up, I actually don't see it as natural to phrase it in the pipe dream complex. I mean, maybe, but I don't have an insight as to how to phrase it well, because the most naive thing of going from a higher to lower dimension by adding crosses is just not true. Here, I can go from here to here, but not by adding a cross, rather moving some crosses around and then adding a cross.
I see. That's really helpful. Thank you.
Okay, we're running a little towards the next talk. So there are a few more questions in the chat, and there was one raised hand. It's gone now.
Yes.
Alejandro, your hand was raised.
Yes. Yeah. So yeah, very nice talk, Karola. Thank you. I had a question maybe also about this. So does the Newton polytope of these Grothendiecks is special because of this nice structure?
Sure. So well, both ways. Yeah. So proving the polymatroid or generalized permutahedra conjecture on Grothendiecks would imply this, and then probably one could go from here to there, but I don't like. It's not like exactly the same, but basically very related. Yeah. But so I guess in our upcoming preprint, which is not up yet, with Linus, Satyabrat, and Avery in this year, we show how to go from the polymatroid conjecture to here.
Okay, so I think maybe for the remaining questions, you can be discussed in the chat while we set up the next talk. All right, so thanks again for the nice talk.